Hey there, and welcome. Let's talk about something in marine automation, a control system that's, well, it's basically obsessed with perfection. It's called integral control. And think of it as this silent hero, right? Its job is to make sure that critical systems on ships don't just get close to their target, but they hit it exactly.
All right, so let's just kick things off with a question. Why is almost perfect such a big deal at sea? I mean, why can't we just settle for good enough? Well, when you're dealing with these massive engines, these high-pressure boilers, and you're in the middle of the ocean, a tiny, nagging error can lead to some serious problems. Inefficiency, or worse, even disaster. So yeah, that's the problem we're going to tackle today.
You got to think of modern ships as these incredibly complex floating cities. And to run them, they absolutely rely on sophisticated automation. These control systems, they're kind of like an invisible crew. They're constantly making these tiny little adjustments in the background to keep everything running smoothly, so you don't need a person staring at every single gauge 24/7.
So, to get a grip on any controller, you first have to understand what error is. And it's a really simple idea. You've got the value you want, we call that the set point, and then you've got the value you actually have. The gap between those two, that's the error. And the controller's entire reason for existing is to make that gap disappear. Simple as that.
Okay, but here's where things get a little tricky. See, some of the simpler control systems, they work really hard to get rid of that error, but then they kind of get lazy or comfortable. The system settles into this new balance point that's close to the target, but it's not on the target. So the error gets smaller for sure, but it never completely goes away.
And this annoying, lingering problem, it actually has a name. It's called steady-state error. It's basically an offset that just hangs around. I mean, the system is stable, right? It's not bouncing all over the place. But here's the kicker. It's stable at the wrong value. This is that exact, almost perfect problem we were just talking about.
And this here makes the problem totally clear. Let's say your engine's cooling water has to be exactly 80 degrees Celsius, but the system decides, 78 is close enough, and just settles there. That 2-degree difference, running day in and day out, that's your steady-state error. And yeah, it might seem small, but believe me, over a long voyage, that adds up, and it really, really matters.
So what do we do about this stubborn little error? How do we fix it? Well, we need a smarter kind of controller. We need one that doesn't just react to what's happening right now, but one that actually has a memory. And that, my friends, brings us to integral control. So unlike a really basic controller that's only looking at the error at this very second, integral control, or iControl for short, it takes a totally different approach. Yeah, it's watching the error, but it's also doing something else in the background. Something way more powerful.
And here it is. This is its secret weapon. This controller remembers. It adds up the error over time. You can almost think of it like it's getting more and more impatient. The longer that error just sits there, refusing to go away, the more determined the integral controller gets to finally crush it.
And what's so powerful is its logic. It's so simple, but it's totally relentless. Check it out. If an error exists and it's not going away, the controller's action doesn't just stay the same. Nope, it gets stronger and stronger. It just keeps pushing and pushing with one single-minded goal. Make that error hit absolute zero. End of story.
Okay, to really get how this works, let's use a super simple example. Filling a freshwater tank. I promise, this will make the whole thing click.
All right, so let's imagine our target is 100 liters. The water gets up to 90 liters, and it just stops. Now, a basic controller might just call it a day right there, but not our guy, the integral controller. It sees that 10-liter error just sitting there, taunting it. So it waits, and as time ticks by, it starts to slowly nudge the inlet valve open just a tiny bit more, and then a little more, until bam, that tank hits exactly 100 liters. It absolutely refuses to stop until the job is done perfectly.
And that relentless drive for perfection is exactly why integral control is such a total game changer in marine automation. It's built for one mission and one mission only.
Okay, so it's not a silver bullet, right? It's not perfect. Because it has to remember the error over time, it can be a little slow to get going at first. And if you make it too aggressive, what engineers call tuning it, it might actually overshoot the target. It could even make the system wobble back and forth like a pendulum. So yeah, it definitely needs to be balanced just right.
But even with those potential drawbacks, the one thing it does, it's so incredibly important that it's become an essential piece of pretty much every sophisticated control system out there.
This right here, this is its superpower.
This is its entire reason for being. It eliminates steady-state error. It's the only type of control that can, all by itself, guarantee that the final error will be zero. It literally hunts down that last little bit of error and just destroys it.
And look, this isn't just some textbook theory. Check out these real-world applications on a ship. You talk about a boiler's water level, being even a tiny bit off is seriously dangerous. Or fuel oil temperature, get that wrong and you're talking bad combustion, wasted fuel. For these critical systems, close enough is a recipe for disaster. You need absolute dead-on precision.
So we just said integral control can be a little on the slow side. So how do you get that precision without the slow start? Well, the answer is simple. It almost never works alone. It's a team player.
And that team is called the PID Controller. Honestly, this is the gold standard, the dream team of industrial automation. It stands for proportional, integral, and derivative. And each member of this team has a very specific job.
This chart lays it out perfectly. First up, you've got P for proportional. Think of this as the fast-reacting sprinter of the team. It gives you a quick, immediate response to any error. Then you've got our specialist, I for integral. We know this one. It's the perfectionist that comes in to wipe out that final error. And last but not least, D for derivative. This one's like the fortune teller. It predicts where the error is going, acting like a shock absorber to prevent overshoot and keep everything stable.
So when you put all three of them together, what you get is a control system that's fast, super stable, and incredibly accurate. It's literally the best of all three worlds, all working together in perfect harmony to keep a ship's systems running flawlessly.
All right, let's wrap this up. What's the big takeaway here? What does all this really mean out there on the high seas?
Look, if you remember just one thing from all of this, make it this. When you hear integral control, I want you to think of the number 0. Its whole purpose in life is to get to 0 steady-state error. That's it. It makes sure the systems we count on for safety and efficiency aren't just close to the target, they are exactly on target.
Because at the end of the day, out on a modern ship, precision isn't some kind of luxury. It's an absolute necessity. And it's all made possible by these incredible invisible systems. It's the silent, tireless work of controllers that remember the past so they can perfect the present. Thanks for tuning in.